Our next speakers are Ken Jean and Jules Poon, and they will talk about how two undergrads from the other side of the planet are speeding up your future code. Let's give them a round of applause.
Okay. Hi, I'm Kenjin, and she's Jules. We're really glad to be here today to give our talk on how we're making Python faster in the future. This is our first PyCon US, so we're really excited to be here. Thanks for having us. Okay, before I forget introductions, we both flew here all the way from Singapore, so as you can see, it's not that close to here. And I'm Kenjin, a university student, CPython core developer since 2021, and a part-time software engineer at Quantsite Labs. Sorry.
Okay. Yeah. And I'm Jules, currently a mathematics undergrad, interested in algebra and programming languages.
We're not here to sell you a product of some sort. Instead, I'm here to tell you of our ongoing work to make CPython faster. So this is our goal. Before we get into the details, here's a brief timeline of our involvement. Before we started university, I was part of the effort to make CPython 3.11 25% faster. And after university started in early 2023, I approached Jules to take a class on programming language implementation. This was because the module was project-based and will give us an excuse to work on something we actually liked while earning some academic credits. Later on, we got even more academic credits by using this period as our summer project.
So it was during this period we started on the first experiment to write an optimizer for CPython. Over the course of about half a year, we implemented a technique called lazy basic block versioning by Maxim and incorporated Brent Butcher's copy and patch cheat. This was just an academic pursuit for us to experiment with various optimizations and discover challenges associated with our goal. In the second half of 2023, we worked together to experiment on possible optimizers for CPython bytecode. As for me, I unfortunately left the project in December 2023 due to my personal circumstances and mental health. And Kenjin wrote the final version of CPython's optimizer that landed in Python 3.13. So it is this final version that will be the topic of our presentation. Now, before we get into some of the details of the optimizing pass, we'd like to establish some background about CPython internals. We have attempted to make the technical part of our presentation as accessible as possible, so we hope you gain something out of our presentation, even if you're completely new to programming language implementation. So, what is CPython? CPython is the reference implementation of Python, and what that means is that if you have installed Python from the official website and run your code on it, CPython is the program that's running our code. The C in CPython is a reference to how CPython is written in the C language. So CPython is what we call a bytecode stack machine. These are a lot of terms to unpack, so we will just go through one by one. So first off, bytecode is a form of instruction set that is designed for easy interpretation by an interpreter. You can think of bytecode as a sequence of instructions that the interpreter runs. The reason why bytecode exists is because it is way easier for the interpreter to execute bytecode than it is to execute your Python code directly. However, we still need a way to convert your Python source code into the bytecode that the interpreter can understand. For this, we need a component called a compiler. This translates Python source code into bytecode. And CPython is a compiler interpreter packaged into one. When we say that CPython is a bytecode stack machine, the bytecode refers to this fact about Python. Secondly, the stack in bytecode stack machine refers to the stack data structure. Yeah. And the reason why CPython interpreter is called a stack machine is because it uses a stack to store its intermediate results. Relatedly, the majority of CPython's bytecode are instructions instructing the interpreter on how to push or pop values into or onto the stack. Now we think it would be helpful to show an example of CPython bytecode in action. So we consider this expression, and it gets compiled into the following CPython bytecode. And now you're going to trace through the execution of the following bytecode. So first off, you load the first two values A and B onto the stack. Then the plus operator would pop both values from the stack and push the result of the addition onto the stack. And we do the same for C, and we get the result of the operation at the top of the stack. So if you notice, the bytecode here is generic, and that's the case for quite a lot of CPython bytecode. And that means that it works for all types of values. In our case, A, B, and C can either be a string, integer, or float, or even an object. For each type, the bytecode has to perform something different. This means that some of the bytecode, in this case binary op, has to perform type checks and dynamic type dispatch. Sometimes other overheads are also involved, which makes it quite slow. So one major change in CPython 3.11 that made things faster was a component called the specializing adaptive interpreter. This component observes the types a bytecode encounters at runtime in its input stack variables. If a bytecode consistently encounters a certain type, it rewrites itself to a faster version of said type. This allows specialized bytecode to avoid unnecessary computation required for handling a generic object, and this makes it faster. This specialized bytecode is also referred to as the tier 1 bytecode, and we'll occasionally use this terminology in later slides. So tier 1 bytecode might also cache intermediate computations to avoid expensive recomputations, such as expensive lookups like getting an attribute. So in our previous example, if for instance A, B, and C are consistently integers, our previous binary ops gets overwritten to the following, which specifically handles integers. Furthermore, the load global gets specialized into load global module, which takes advantage of some form of caching to avoid searching the globals again. This often produces quite a significant speed up in cases like calling a Python function or loading an attribute. So if you want more information, you can actually view Brent Butcher's talk from last year about the specializing interpreter. In 3.11, the bytecode optimizations only occur across 1 or 2 instructions, but in 3.13, optimizations take into account larger regions of code, which allows us to use more information about the surrounding code to make more ambitious optimizations. The key observations that other language runtimes also realize is that you can use the types you learn at runtime to do larger region optimizations. This was pioneered back in the Self language and is used commonly in JavaScript like VA, IronMonkey, and WebKit, and even other implementations of Python like PyPy. So it's not a new idea at all. The tough part is implementing it correctly and safely in CPython while also not increasing maintainer burden. So now I'll be passing it on to Kenjin to talk about the work that went into CPython 3.13 and the work that is planned for beyond.
Thank you. So CPython 3.13 currently ships with an experimental JIT. The optimization pipeline is shown here. CPython currently does not build with the JIT on by default, as while it provides speed up in some applications, it slows down many others right now, in addition to taking up a bit more memory. A lot of it is work in progress and will only appear in CPython 3.14 and beyond. As of right now, we don't recommend using the JIT compiler in production, but please help us test it out. So yeah, thank you. Linear optimization pipeline is CPython 3.13 is often simply referred to as the just-in-time compiler. And this is the case for JITs in general, but this is a bit of an unfair generalization because a JIT compiler has multiple separate parts that can differ greatly between implementations and usage. People often tend to think of these entire systems as one magical solution to make things faster, which is not true in general. For CPython, an important thing to keep in mind is that just throwing a JIT does not necessarily mean the result is faster. Therefore, the two components that precede the JIT, which is the optimizer and projecting tracers, is necessary for us to make CPython faster. This is a high-level view of everything. What you saw now in the specializing interpreter just now is now called tier 1. It's translated to tier 2 tracers and then optimized by the tier 2 optimizer before being compiled by the machine code generator, or as we confusingly put it again, the JIT compiler. So now let's talk about the first stage in the pipeline, projecting tracers. As of right now, if you build CPython 3.13 with the experimental JIT turned on, the first thing that the pipeline does is project tracers or specialized bytecode. This means that after the specializing step has completed, the pipeline will predict execution based on the frequency a branch is taken. Traces are just straight-line code sequences. There are no branches in a trace, such as if-else, other than a jump back to the top. This is because during execution, only one path is predicted. We start a trace on the backwards edge of a loop. As the trace records execution, the specialized bytecode gets broken down into smaller units, which we call micro-operations. These micro-ops allow us to identify repeated work done across multiple instructions. What this means that will be made clearer later, but in this case, 4-iter range gets broken down into the following 3 micro-ops. So the trace starts at the backward edge, bytecode gets broken down here, and as you can see, 4-iter range gets broken down to that, and then we break down each operation one by one. until we hit a backwards edge that closes the loop. In general, the trace stops when this happens, or if it becomes too long or too unwieldy, we also stop the trace. Now, these traces will then be optimized, and this step is the main objective of our project. Here's the overview of the optimization step. It consists of multiple passes, and I'll only cover 2 of them today. The first pass is written by Mark and already implemented in CPython 3.13. We promote globals to constants. Objects that the trace accesses in the global scope get burned into the bytecode, making global lookup a little cheaper as we don't have to index into the globals. The next pass contains stronger optimizations, and this pass was written by me with help from Mark, Guido, and Peter. The current plan for this pass is to perform guard elimination, true function inlining, deferred object creation, otherwise known as scalar replacement, register allocation, top of stack, also known as top of stack caching, and the main analysis that enables these optimizations is an abstract interpreter that has been implemented in CPython 3.13. As for CPython 3.13, guard elimination has been partially implemented, but the rest is planned for 3.14 and beyond. These are big words, so let's break them down. CPython 3.13's data flow analysis uses a technique called abstract interpretation. In normal interpretation, you interpret bytecode, and the values you operate on are Python values and objects. In abstract interpretation, you interpret bytecode as usual, but operate on abstractions of Python values and objects. For example, you can operate on the type of an object. I'm hand-waving a lot of math here, so if there's any compiler folks in the audience, I'm quite sorry. The cool thing is that the vast majority of the abstract interpretation pass is actually automatically generated. We use CPython 3.12's interpreter generator, and it's a custom mini language inside CPython used to specify the interpreter. Yes, you heard that right. It's a language used to create another language. We don't have time to go into it, but it's a real cool piece of tech. This also lays down the foundations for significantly more optimizations in the future. That was what was done in 3.13. Of the 3 that we planned for, only the first one has been done partially, and the rest is aimed for 3.14. The first one that is partially done is guard elimination, and what this means is that every time Python executes specialized bytecode, it needs a guard to check if the types match or if our assumptions hold true. These are usually quite cheap, but if we can eliminate them, why not? For this, CPython 3.13 uses a type information collected during the abstract interpretation pass. If it sees that we already know the type of something, we can just eliminate the guard. For example, after the first type check, we know that B is an integer, so the next type check is no longer needed. The last type check is also then converted to a cheaper type check that only checks for A. More information is propagated, not just types. We also pass constant values in the analysis. For now, it's just Boolean constants that are eliminated, but in the future, if you have something like this, and there are known constants, the whole expression can actually be folded into a single constant addition. The next optimization we want to perform is true function inlining. This was worked on by me, but then put on hold. The idea is that essentially every time you call a function, there's some overhead involved. You could copy-paste the body of a function into your code, but that's not very clean code, is it? So instead, we do it for you. Once the trace is formed, the bytecode optimizer will see that these 2 instructions that push and pop frames. Frames are activation records of a call. They are used to keep track of a call. This is where most of the overhead lies. If the frame fits some predetermined guidelines that we use to inline, we can then remove the frames altogether. This removes the overhead of 1, creating a frame, and 2, copying your arguments over to the new frame. My own experiments for this suggest that a roughly 30% reduction in function call overhead. In fact, with more optimizations, the preliminary experiments suggest that the overhead of a call through Python will almost be as low as calling a C extension function. So the next one is Mark Shannon's idea, and I'm not particularly sure where this term was first used in CS literature, but a similar idea is called scalar replacement. The main idea in deferred object creation is if we can defer the creation of an object or not create an object at all, then let's do that. For example, if you have something like the first example here, it should just return 3 directly without creating the list object. Another example is, let's say you have a filter function. The initial list literal should not even be created, although we still need to create a filter object and list internally. So in 3.14 and beyond, there's register allocator and a top of stack caching. This works by brand, and remember that stack from way earlier. Well, every time you read and write values to it, there's a cost to that. we like to remove that cost. So instead, we can cache the top few values of the stack in local variables instead. And this nets us roughly single-digit wins on some benchmarks for a preliminary result. The last part is the JIT compiler. And this part was already covered by the talk right before ours by Brent Booker, so sorry if you missed it, but we won't cover it again. You had to watch the talk before or just travel back in time. The main idea is that we pass the generated traces to a machine code generator. So you might ask, what if a guard is needed because type change? What if I need that function frame? What if I need that object? Well, this is called side exit and de-optimization. In the happy path, we assume that we can rev up the engine and do all sorts of awesome optimizations. And we check for unhappy events. If these events occur, we reconstruct the entire state of the interpreter and exit out of the current trace, either to another trace or to tier 1. And this was mainly implemented by Mark. For side exits, these are normal events that happen when we want to create another trace. We either jump back to tier 1 or create a new trace if the exit is hot, or jump to an existing trace. For example, in the following function, it creates a trace assuming the inputs are integers. If you pass in a float the next time you call the function, the guard top of stack integer bytecode will fail. Once the exit gets hot enough, we create another trace. If not, we fall back to tier 1. This actually forms a tree of traces. For a de-optimization event, we drop out of the entire trace back to tier 1. This indicates a really rare event has happened. Okay, so that was a lot to cover. Now Jules will cover our involvement in the project and how we came to all this.
Okay, so as briefly covered in our intro, Kenjin started on CPython before university, and in the first semester of university, we were basically really bored. So, and Kenjin found this cool class on programming language implementation that has a major project component, which we wanted to use to work on CPython. And since the professor really liked programming languages, he agreed to supervise us for our project on hacking on a fork of the CPython interpreter. After that, our school had a summer software engineering project course where you could work on anything you want, and we chose again to work on the CPython fork even more. Later on, we found another professor at our university who became a year-long advisor for the rest of our work, leading to what we did today. His experience really helped us when we were stuck on theoretical concepts. So this brings us to like lesson 1 of how to contribute to CPython as a university student. Make full use of whatever resources you have as a university student. Oftentimes, you can benefit from the help and advice of others. So find someone who you think would enjoy working on what you're working on, which could be a professor, advisor, or a friend, and hopefully everybody has fun. In terms of the classes we took not just programming language implementation, but also a bunch of other classes like compiler design. And for Kenjin, he took principles of program analysis. Personally, compiler design gave me the foundations of data flow analysis, and for Kenjin, principles of program analysis helped him to build the theoretical foundations he needed for the optimizer. So this brings us to lesson 2 of how to contribute to CPython as a university student. If your university has classes that help you in your open source journey, consider taking them. If your university doesn't offer these classes, there are plenty of great online resources by other universities who upload their course materials, and we use a great deal of them. Another thing to keep in mind is that open source contribution is not just about writing code. We didn't mention this earlier, but Kenjin actually started off writing big chunks of documentation initially for CPython. And so CPython contribution specifically can constitute stuff like writing code, writing documentation, designs for the CPython website, CI/CD, DevOps, or infrastructure, and a lot more. So keep your mind open.
Jules and I wrote 2 versions of the optimizer, and I then rewrote that 2 more times. This experience gave me the skills I needed to write what I did for CPython, and it would not have been possible for me to write the optimizer I did for CPython had I not gone through those prior projects. This brings us to the final lesson of contributing to CPython as a university student, and this actually applies to everyone, not just students. Be patient with yourself, because results might not come in days, weeks, even months, but you have to be patient because there's a lot to learn, a lot to experience, so take your time. And that's a wrap. Thank you for listening to our talk. I will try to graduate. Jules says she has no plans, so yeah, thanks PyCon US.
All right, we have a couple of minutes for questions, so if anyone has some, please approach the microphone and ask one.
Hey there, can you hear me?
Yeah.
Yeah, very nice talk. My
Thank
question for you all as university students is it better to just get started, or is it better to have the theoretical framework through classes first before you get started? You know what I'm saying? Yeah.
Okay, I'll take this, I guess. Okay, so the thing is, you can do either ways because getting started will teach you the theoretical frameworks over time. So I don't really see a difference between the two. Just do whatever you're comfortable with. I personally started with getting started before getting the theoretical foundations.
Thank you. Thank you.
You're welcome.
You mentioned getting the most of the experience as a university student, how to restructure your expectations or what have you. Do you have any suggestions for the projects for how they can restructure themselves to be more accessible to enthusiastic university students like yourself that may be in a position to help?
Do you have any idea? That's a really tough question. I'm sorry, I don't think I can answer that question for you because I'm not. I don't, do open source engagement at the moment. Yeah, sorry about that.
No worries.
This is great talk. Thank you to both. I have a quick question on the optimizer. I wonder if there is a timeline or a plan to define a context for the optimizer so that we can not only do per micro-op optimization, but scan through a whole sequence of micro-ops, for example, for the entire function so that we can do the optimization at once.
Wait, sorry, I don't really understand the question. Could you try to rephrase it, please?
My question is about the context or the scope of the optimizer.
Right.
Right. Like how many ops can we optimize at once?
Okay, so the trace, it actually optimizes the whole trace at once. And trace right now is slightly around 800, like roughly 800 bytecode instructions. That's the max size of the trace that it can grow to. So we do optimize more than one bytecode instruction at a single time.
I see. But it's not like a per function optimizer.
The regions that we optimize are traces, not per function. But in the future, functions can be traced from the entry as well. At the moment, we only trace true functions, but only if they occur inside a for loop or while loop.
Okay, thank you so much.
So I think that, like many others, I'm very excited about all these optimizations coming to CPython. And what I wanted to ask you is, do you have an idea of what kind of workloads get optimized with faster speedups? I don't know, like workloads with a lot of data classes or pandas or other patterns and use cases of Python?
Well, if you spend a lot of time in third-party extension C libraries, the speedups won't be that great. So pandas probably not. But if you spend a lot of time like in data classes or in pure Python code, it should speed up in the future.
Thank you.
Yay. Okay.